Hello, my name is Laura Mazzoni, and in this video I will present the results of the paper Immersive Learning in Teaching Geomatics for Engineering Students. Topography is responsible for the acquisition, analysis, and management of spatial data to describe the surface characteristics of land area, and it is a basic discipline for several courses, such as civil, environmental, petroleum, and mining engineering, as well as architecture and geology. To learn topography, students must use a total station, the equipment here in this image, to collect field measurements. However, the total station is an expensive equipment and requires maintenance. In addition, adverse climate conditions, such as rainy days, make field measurements impossible. Also, some students do not operate the equipment, since measurements are collected in groups. Two VR applications were developed for training topography students. Sprint 1 consists of introducing the total station, and Sprint 2 simulates real field activities. Here in this video, you can see how these activities are performed using VR during classes. Now introducing Sprint 1. The module begins with the students entering the virtual reality environment, which simulates the interior of the faculty building. From this point forward, the student will perform basic orientation and navigation tasks within the virtual space, followed by procedural operations related to detail point collection using a total station. The experience begins with an overview of the VR controls. The students learn to interact with the environment using basic hand functions, such as grabbing objects, selecting items, and navigating through space via teleportation. After familiarizing themselves with controls, the students proceed into a sequence of tasks simulating real-world procedures. First, the student must gather all necessary survey equipment and accessories such as pickets. Thus, a survey picket must be positioned on the ground, marking the initial reference point. Next, the students retrieve the tripod and carefully position it over the survey picket, ensuring the tripod head is approximately centered above the point. In the next step, the student adjusts the tripod legs to ensure the tripod head is approximately level directly above the reference point, providing a stable and accurate setup for the total station. Prior to the setup process, the student must remove the total station from its protective case. Subsequently, the total station is mounted onto the tripod head, ensuring that the instrument's base aligns precisely with the mounting plate. With the instrument properly seated, the student powers it on and begins the electronic leveling procedure. This involves adjusting the leveling screws to achieve accurate geometric alignment. Additionally, a laser plummet is employed to ensure precise centering over the serving point. Visual guides and animation reproducing the total station screen is a zoomed-in view support this process. Once leveled, the total station is prepared for use. The student activates the measurement mode and is introduced to the virtual viewfinder, simulating the device's optical alignment. To simulate a real measurement, the students adjust the station horizontally and vertically to collimate at a target, and then records the first measurement by pressing the virtual button Measure. Here we are presenting the Sprint 2, which simulates the external area of the faculty building. This module introduces a more comprehensive set of activities. Upon selecting Continue on the initial panel, it is indicated that the tail point will be measured from point A. Thus, the students must move to point A. The total station has already been positioned at this location. The total station must first be attached to the tripod head and then electronically leveled and centered. These steps follow the same procedure performed in Sprint 1. Once leveled, it is ready for measurements. To establish angular orientation, The student identifies and collimates at the point Pi as backsight point. By sighting the total station at Pi and selecting measure, the backside data are recorded, including distance, horizontal angle, and vertical angle to Pi. Subsequently, the students proceed with the collection of foresight data at the detail points. In this example, the detail point is a tree. To get data for this detail point, the students must collimate the total station at the base of the tree, not at its center, to obtain the correct height, and select your measure. The corresponding data are then recorded in the table: distance, horizontal, and vertical angles. And this concludes the demonstration of the Sprint 2. An expert evaluated both sprints and highlighted the lack of initial steps for training students with VR control, especially the teleport function. The students evaluated the experience by responding to a form for each sprint. Over 50% of students had never used a VR headset before, indicating a lack of familiarity with it. 25% of them reported some discomforts during the use, such as headaches or dizziness. Over 80% of students had no or slight difficulty completing the sprints, and over 95% of them evaluated the experience positively. However, students also reported problems with the teleport functions and control. We conclude that the experience was well received by students and it was adequate for teaching topography. It also allowed the students to engage with virtual serving tasks, offering a controllable and repeatable learning experience. The limitations are related to discomfort during prolonged use and difficulty navigating the virtual environment, which can be reduced by improving the instructions. And these improvements must be considered for future implementations in geomatics and other related courses, such as road design and traffic engineering. Thank you for watching the video.